Okay, so welcome back. In the previous videos, we described what the relationship between forces and motions are, essentially Newton's second law of motion. And we'll see a lot of examples how that will work. But now I want to bring your attention to a few of the types of forces that can, or types is a bit of a stretch. A few usual cases we deal with forces, certain characteristic forces that we deal with. Maybe that is better. The first one is gravity. Again, for the sake of discourse, we go back to classical Newtonian mechanics. And this is actually Newton's law of gravity. By observing motions of planets and stars, he came up with this. And in this view, if you have two bodies, one of them having mass m1, another having mass m2, and they are some distance r separate from each other, just because they have mass, they exert force on each other. Again, remember third law. M1 exerts force on M2. M2 exerts the same force, opposite direction on M1. And this force, the size of it, and let's start with direction. The direction is along the line that connects the two masses together. So direction is along the line, always, at least the way we know it, attractive force. And the magnitude of F is related to mass of the particle, m1 times m2. It is inversely related to the distance. So as you go further, the size of the force becomes smaller, and there is some constant in front of this equation. This one is called constant of gravity. Gravitational constant. It has some value. Let me see what it is. It is really, the value doesn't matter that much. It is 66.73 10 to minus 12 meter cube by kilogram second squared. Is the unit correct? Probably not. No, it should be the other way around. Yeah, it should be the other way around, I think. Why did I write this equation? Probably should be... Oh, sorry. Meter cube, kilogram, second squared. The 2 meters... No, this is good. Yeah, this is good. Sorry. I confused myself. Unit is this. Anyhow, long story short, gravity is an attractive force between two bodies that have masses. The force is related to the two masses, inversely related to the square of distance, with some constant of gravity. Gravity is a very weird force. I don't know, don't quote me on that, but it is still not fully resolved what gravity is. It goes deep into relativistic view, what Einstein came up with. But even that is still, I think, not fully resolving what gravity is or where it comes from. Anyways, that's not my business. I use gravity to calculate simple forces. What else did I want to say? Oh, gravity is a relatively small force compared to other forces we experience. So, for instance, a person that has a mass of, I don't know, 70, 80 kilos attracts another person of similar mass. They exist, but the size of that force is so small that we always ignore that in our calculations. We do not discount the effect of gravity on Earth because we consider the attractive force of the Earth on a person, and because mass of the Earth is so huge compared to other masses, that accounts for something tangible and we can kind of feel it in our days, every day. But you should know that gravity is relatively small force, at least for masses that we deal with in engineering solution. There's another form of this equation. This is general law of gravity. Gravity of Earth. So if one of these two bodies is Earth and the other one is a mass of some, let's call it m, the force of gravity of Earth on this particle, we can calculate it exactly the same thing. F is mass of Earth, mass of this object, divided by radius of the Earth squared times g. And we are more comfortable to combine all these three quantities that are relatively constant. Mass of the Earth is mostly constant. The constant of gravity is constant. Radius of the Earth, depending on where you are and how far you are from the surface of the Earth, that can change. But with distances not too far from the surface of the Earth, that RE can also be considered constant. So I have three constant values. We can calculate that and give it a different name. Let's call it little g. And in this case, force of gravity becomes mass times this little g. And this is the familiar form that you may have seen before, or sometimes we call it W for weight equals mg. And that is weight of the object. A few things to note here is that this g is only for Earth and for objects that are relatively close to the surface of the Earth. Standard g is 9.8. I had the value. Let me see. 980,665. The unit is meter per second squared. This is called the standard G. And you multiply by the mass of the object to get the weight. A few things to remember or note about this is that, first of all, G is not constant. It is different depending on where you are on Earth. The Earth's mass distribution is not completely uniform. So G is a little different in every location. Another thing, depending on how far you are from the surface of the Earth, obviously the gravitational pull is going to be slightly different, but for engineering practices, it's a good approximation. Usually we go with two significant figures, 981, or its equivalent 32 point something in the imperial system. But note that these are approximations. These are not exact values of gravitational pull of the Earth. Another thing I want to mention, this is also called gravitational acceleration. First hint is that it has a unit of acceleration. Also, if you note that if this is surface of the Earth, you have an object falling through gravity. If there is no other force acting on it, only force of the weight, which we calculated, it is mass times gravity. If you write the Newton's equation of motion, Newton's second law, you have the force, W equals mass times acceleration, and W is mg equals ma. So the acceleration that the particle will have equals this g. So that's why it's called kind of gravitational acceleration, because it is the acceleration of a free falling object on Earth. Yeah, I think that is all I wanted to say about gravity. Takeaway messages: in engineering practices, we go with this simple equation to estimate the weight of a particle, but note that weight is related to gravitational pull between the Earth and that object, and it changes based on a lot of things, most notably with the distance from the center of the Earth. And yeah, I think that is all I wanted to say about gravity. So we look at two other forces in the next videos and we wrap this section up. So I'll see you there.